Hi, everyone. Welcome. This is Malikeh. I am ML Research Scientist at Vector Institute. It's a pleasure to be here. Firstly, I wanted to say thanks to the Neptune AI team and MLOps World Gen AI Summit for organizing such an amazing webinar. It's a pleasure to be part of it. So as you can see from the title of this presentation is Scaling Down, Powering Up, Can Efficient Training Beat Scaling Laws? So here in this talk, I plan to first do a historical review of what the scaling laws really mean, and then invite everyone to rethink the scaling paradigms. And together we explore the future research directions in the field. So I start the talk with this question: is AI scaling hitting a wall? This is the question that many of us may have asked ourselves. So if you've followed AI circles, you've probably heard about the scaling laws. And the idea is basic. The more data you have, the bigger your model, and the more compute you use, the better your results. But recently, some experts think we might be hitting a plateau. It's a lot like working out. At first, every extra hour at gym makes a big difference, but after a while, the progress starts to slow down. So in late 2024, if you look at the news channels, we see scaling optimism turning to skepticism somehow. So we have this headline from CNN Business stating that AI is hitting a wall just as the hype around it reaches the stratosphere. And then we have Reuters claiming that OpenAI and others seek new paths to smarter AI as current methods hit limitations. And then we see information stating that OpenAI shifts the strategy as rate of GPT AI improvements slows. Bloomberg highlights OpenAI, Google, and Anthropic are struggling to build more advanced AI, and Time questions whether AI progress really slowed down. And we have this blog post from TechCrunch, the last but not the least. They state that current AI scaling laws are showing diminishing returns, forcing AI labs to change course. So after that, similar to all these authors of this news headlines, we might also question ourselves at where we are with this AI scaling laws. So to answer this question, let's flash back to January 2020, the birthday of scaling laws in neural language models. At the time, language models were a promising area of research, but the current generation of models like GPT, Llama, Qwen at the time had limited capabilities. And we had yet to discover the power of larger models and the path towards creating better models. And that was when this paper from OpenAI was released, the scaling laws for neural language models. And in this paper, they tried to answer the questions that was the question for a lot of people at the time. Is the shape of the model important? Does making a model larger help it to perform better? How much data is needed to train these larger models? So here, the authors try to analyze the impact of several factors on scaling up the model performance: model size, model shape, data size, batch size, training compute. And it was one of the very first analysis of how these scaling laws can be impactful. Many of you might be familiar with these famous figures from this paper. So this is a part from the paper saying that the loss of skills as a power law with model size, data size, and the amount of compute used for training, with some trends spanning more than 7 orders of magnitude. So what they did in this paper is that they fit their power laws. To fit their power laws, what they did was to pre-train LLMs with sizes up to 1.5 billion parameters. They used web text to corpus with something around 22 million to 23 billion tokens. And then they trained their models with a standard next token prediction cross-entropy loss. And here were the results. The performance is steadily improved with more parameters, data, and compute. These trends span 8 orders of magnitude in compute, 2 orders of magnitude in data size, and 6 orders of magnitude in model size. So here now, we had some rules to see how scaling all these scaling factors would affect the final performance. And there were two interesting takeaways from this paper. Larger language models exhibit greater sample efficiency, requiring less data to achieve comparable test loss. And another interesting thing was that dataset growth lags behind model growth. So they stated that an 8 times increase in model size requires just a 5 time increase in training data to maintain performance. So something interesting in that paper is that they highlight that maybe scaling model size is a more important factor to get to where we want to be. But let's see what happened in the future papers. In July 2020, this paper by this paper by OpenAI was out. That's a famous paper. Language models are a few-shot learners. This is when GPT-3 was introduced. It was a major turning point in AI, clearly, because this was one of the first foundation model, or like the first examples showing how powerful larger scale pre-training can be for language models. And yeah, this model was outcome of massive scale up in model parameter size to 175 billion parameters, which was 100 times larger than the largest GPT-2 model at the time. And they pre-trained this model on a data set which was 10 times larger than web text data used for GPT-2. They used Common Crawl, and here you can see the breakdown of data sets they use for training their model. So one interesting concept was introduced in this paper. They introduced things like few-shot learning, in-context learning. So they introduced a new interaction paradigm with the models, and they were not only talking about weight updates, they were talking about better context use. They demonstrated that larger models are better few-shot learners and achieve the state-of-the-art performance across many tasks by just prompting and not only fine-tuning. What I mean by few shot, if you're not familiar, so 0 shot means that, for example, you want to prompt a model to translate a word from English to French. In the 0 shot scenario, you just describe the task, translate English to French, and then give the prompt to ask the model to translate cheese to the target language. But in a few-shot example, in addition to the task description, the model sees a few examples of the task. Here, we can see additional pairs of English-French words just to show the model how this translation can work. And they showed that these better usage of context can be a helpful way of scaling up model performance. But the important thing is that they kind of redefined the scaling from the weighted space to context space. So it was another perspective to how scaling can work. According to VentureBeat, GPT-3 is estimated to cost more than $12 million to train. And later we see Sam Altman stating that the cost of training GPT-4 was more than $100 million, which is huge. But the question is, how can we predict a model's success without breaking the bank? Larger scale pre-training yields the best results. Yes, but it's risky and expensive. And training these massive models can cost more than $10 million, which is, I think, not affordable for many of us in this room, with no guarantee of success. So this is where these scaling laws offer a strategy. They can come into play. You can train smaller models and fit scaling laws to predict larger model performance. This would definitely de-risk larger training runs. And if you want to ask investors to invest in larger scale AI projects, it's a good way of justifying these investments. And another turning point in AI scaling history was the release of this Chinchilla paper. In March 2022, Chinchilla changed the scaling game. So by the time people trained models significantly larger than GPT-3, at the time we had Megatron, Turing NLG, or MTNLG. It was a model with 530 billion parameters. Despite their size, these models were trained on data sets similar size to GPT-3's, and these models couldn't outperform GPT-3. In contrast, models like Gopher with 280 billion parameters were achieving the better performance by both scaling up data set size and also parameter size. However, the important thing about this Chinchilla paper was that they were mentioning that training on more data is also needed, not just bigger models, while the OpenAI paper was firstly saying that maybe scaling model size was important. So here in this figure, you can see that they trained kind of larger models from 70 million to 10 billion parameters, and they trained them over more than 1 trillion tokens to fit their training curves. So as a way of predicting the optimal model and data size given specific flops. Flops is a floating point operations. It's a measure of total number of arithmetic operations needed. And the important thing about that was that, so if you look at these figures, the one in the center shows the optimal number of parameters needed for given flops, and the one on the right side shows the optimal number of tokens needed for the given flops used in training a model. And the green line shows the optimal number of tokens and parameters needed for the flops used for Gopher. Gopher was a state-of-the-art at the time, but the interesting thing here is that they said for Gopher, you needed at least 1.5 trillion tokens, while they only use 300 billion tokens. And then to get to that performance, it's enough to just train as 67 billion parameters, while Gopher was 280 billion parameter. And the main takeaway from this paper was that many of the state-of-the-art models at the time were undertrained. You needed a lot more data to get to the optimal performance you were looking for. So to validate their findings, they trained Chinchilla. It was a 70 billion parameter model trained on 1.4 trillion tokens, significantly more data than the prior models. And despite being 4 times smaller, Chinchilla outperforms Gopher across benchmarks. Here you can see the MMLU results comparing Chinchilla with Gopher, and you can see Chinchilla outperforms Gopher in 51 out of 57 individual tasks, which is fantastic. So for years, Chinchilla Low or Chinchilla Optimal was the gold standard across GenAI projects, and we still use it as a reference when we try to do larger scale training. But again, is AI scaling hitting a wall? What does it really mean? And why is it happening? So we did a review of what scaling laws really mean, but what do scaling laws tell us? So all these scaling laws are defined on top of power laws, mentioning why, for example, the test laws or the performance matrix as a function of X. X can be a scaling factor. It can be model size. It can be data size. It can be compute size. So we see test laws as a exponential function of all these scaling factors. And what is more common in the literature is this inverse power law with negative power. The misunderstanding or maybe misconception when people talk about the scaling laws is that something which is so common in the literature is this logarithmic scale figures showing the relationship between the test laws and the scaling factors. But the reality is that this relationship is exponential in normal scale, and we are where we have to be. So the thing is, in reality, increasing the quality of an LLM becomes exponentially more difficult with a scale. Maybe we are somewhere here, and what these scaling laws tell us is that contrary to some beliefs, scaling laws do not imply exponential performance gains with logarithmic increases in compute. The reality is that they exhibit exponential decay in test laws, meaning that as models grow, each additional unit of compute yields progressively smaller improvements in their performance. So what we are seeing now is exactly aligned with the scaling laws, and we're not far away from the predictions or the expectations. It's just misunderstanding of maybe those logarithmic scale figures. And another question that is very important to ask is that what defines better in LLMs? less test loss. For example, just next token prediction loss using cross entropy doesn't necessarily mean better capabilities. There are many lenses through one model's performance. There are many ways to view LLM performance. This can be from the general capabilities point of view. So it can be LLM reasoning, natural language understanding. This can be from the ethics standpoint or from the safety point of view. And even when we talk about specialized LLMs or domain expert LLMs, the expectations from model performance differ from domain to domain. What you expect from a model in finance is completely different from healthcare. And it's over expectation. If we expect just next token prediction loss with cross entropy can be easily translated to all these dimensions of evaluation. Another thing that you might have heard about is data depth. This is a part from Ilya's presentation at NeurIPS 2024, mentioning that data is the fossil fuel of AI. We've achieved peak data and there will be no more. The thing is, the main data source for most LLM training data is sourced from web scraping. And the thing is, we only have one internet, and the finite nature of high quality, publicly available text data may limit future LLM scalability. We use almost all of the data sets on the net. And the question is, what should we do? So for sure, we have to think about alternative ways of scaling data sets, because especially after the Chinchilla law, we see that the scaling model size is not enough, and we need to scale up both data size and model size proportionally. And this is a limitation if we run out of high quality data. So what's next? In December 2024, this DeepSeek V3 paper was released by the DeepSeek team, and I think it was a glimpse beyond the scaling wall. Despite some doubts, larger scale pre-training continues to bring noticeable improvements. I think it was one of the main takeaways from this release. And one important thing about this model was that it surpassed the performance of GPT-4o. It was a big achievement for the open source community. Even larger models like Llama haven't reached that level yet. So that sounds like, as I said, a glimpse beyond the scaling wall. Again, this model was an outcome of larger scale pre-training. It was a mixture of expert 671 billion parameter model with too many experts. They used some very nice model architecture design. They used multi-head latent attention mechanism as an extension of their V2 paper. And again, they did a larger scale pre-training on 14.8 trillion tokens. However, the budget was comparably tiny, just $6 million compared to the other state-of-the-art models. It was the outcome of 2 months training, very efficient FP training, and very careful, good data engineering. So yeah, here you can see an overview after model architecture. The thing is, what we can see as the main takeaway of this release is that still, as I said, the biggest key to DeepSeek V3's impressive performance is pre-training scale. This is a massive model trained over an equally massive data set. So here you can see an overview of the pipeline of training this model. It starts with larger scale pre-training and then additional post-training. And I really want you to pay attention to some keywords in training this model: synthetic, chain of thought, lots of data, supervised fine-tuning, reinforcement learning, reasoning, distillation. So these are all key steps and key parts in training their model, both V3 and R1 after that. So one more important takeaway from this release was that these results indicate that larger scale pre-training jobs are becoming increasingly manageable and efficient over time. And maybe what we need is data-centric and model-centric efficiency. So $6 million is still significant amounts, but it is considerably more economical compared to other options. That's why we heard NVIDIA corrected its GPU pricings. And maybe these are some initial steps toward the next significant jump in the AI scaling. And one option maybe for the next jump is to just scale up by an order of magnitude. Yes, that's one way to do that. This is a quote from Ehghaghi from Epoch AI mentioning that at every order of magnitude to scale up, different innovations have to be found. So yeah, that's one way to do that. Another thing is that I mentioned pay attention to the, for example, synthetic data part in the DeepSeek release. So synthetic data is increasingly used to train language models these days. And this is, for example, a screenshot from a paper released by Microsoft team last year, which was called Agent Instruct. So in this paper, they use an agentic workflow to synthetically generate data. What they do is that they're using that workflow to turn raw sources of data like text and code into instruction data, and then they train Mistral 7B on 25 million prompt response pairs, resulting in Orca 3. And Orca 3 at the time could outperform GPT 3.5 Turbo and Llama 8P Instruct. So these are interesting examples of how just scaling up synthetic data can help with scaling up model performance. And we can also switch to some, instead of pre-training from scratch, try some continual pre-training strategies with some different tricks. So this is a screenshot from one of the papers from our lab, Efficient Online Data Mixing for Language Model Pre-Training. So what they're doing is a very simple trick. So over time, they change the data mixture ratios of data domains or data groups used in training the model. And with that, they could achieve 19%, achieve the performance with just 19% fewer training iteration, which is fantastic. And another thing is, for example, just simply apply instruction pre-training. These are screenshots from a paper shared by Microsoft research team last year. So what you're doing is that instead of just using raw text during pre-training or continual pre-training, you can mix the raw text with instruction data. And this would help to boost the performance, both the pre-training performance and also to have a smoother instruction tuning process. So these are all the tricks to make the most out of it. And they're all data-centric efficiency approaches that can come into play. And it's not needed that we just limit ourselves to one models. What if we scale from one to many language models? So this is a screenshot from a paper from Together AI team. It was released last year, and this is the title of the paper is Mixture of Agents, Collective Intelligence of Language Models. So they're talking about LLM systems after the rise of small language models and LLM agents. So we can, what we can do is that when a query or question comes from the user, I can decompose that into subtasks and then route these questions to a specific expert LLM. So here at each layer, we have some language models collaborating together in parallel. And then we put a chain of language model calls back to back to get to the final answer we want by just an aggregation mechanism. So this is when a group or collection of language models can work together to get to some collective intelligence. So scaling up is now not at the level of one model, but to scale up the number of many language models. This is another perspective to AI scaling. The last but not the least, the question is reasoning unlocking new scaling paradigms? So especially after the release of OpenAI 01, we heard a lot about thinking, overthinking of these language models, saying that when the model is going to answer your question, let's let it first think and then respond. So one interesting thing in this release was that they found that the performance of 01 consistently improves with more reinforcement learning, train time compute, and with more time spent thinking, test time compute. So the scaling mechanism and the scaling perspective is different in these approaches. So they're not talking about pre-training scale up. They're talking about the scaling up the post-training phase, train time compute for reinforcement learning, and they're talking about scaling up the inference time compute to let the model think more. So there are many papers released that are talking about, for example, chain of thought prompting. It would improve the reasoning capability of the model. If you ask the model to share the step-by-step rationale behind the answer which is provided by the model, or when we ask the model to self-reflect, reflect on its own generated response, it would result in better responses. So in O1, when the problem comes in, the model tries to break down the problem, try various strategies, catch and correct responses, and this would definitely boost the performance, not just by scaling of model size and data set size for pre-training, but also scaling up at the post-training and inference stages. So as I mentioned, yeah, that's true. Several factors contribute to the recent criticism of scaling laws: the natural decay in the scaling laws, the high variance in expectations of LLM capabilities, and the latency of larger-scale interdisciplinary engineering efforts. However, the issues are valid, but the scaling is still effective. Larger-scale pre-training investments will continue, though improvements will become a bit harder. And alternative areas like agentic systems, like reasoning, will grow in importance. Scaling will remain central, but the real question is, what will scale next? So maybe we just need to find new perspectives on scaling LLMs and ask ourselves that, what are the new approaches to scale up? It's not all about pre-training. There are many different ways to do that. Thank you so much for your attention. I hope you enjoyed the presentation. So these are the links to my personal social media accounts. If you have any questions, you can follow up there. Also, we released this podcast, Women in AI Research Why podcast, in March. This is a podcast dedicated to celebrating the remarkable contributions of women AI researchers from all around the world. If you're interested in partnership, sponsoring, or being a guest, feel free to reach out. Here you can scan the QR code and you can find us on LinkedIn, YouTube, Twitter, and Blue Sky. So thank you so much. I think we have a few minutes left for questions. I'll be glad to answer if there are any. So yeah, I see a question here asking, how does a mixture of agents differ from a mixture of agents, or using a larger LLM in terms of scaling with compute, assuming flops are normalized across all three? So yeah, there's always a confusion between mixture of agents and mixture of experts. When we talk about agents, first of all, there are different definitions about agents, but agents are usually language models with extended capabilities of tool use, function calling, so they can take actions other than just generating responses. And when we talk about mixture of agents, it means that, okay, your query comes in, for example, you want to book a flight, and then there would be a router, and this router, depending on, for example, the difficulty level of your question, or depending on the domain of your question, it will route your question to that specific agent. So maybe you can have two different LLMs. One is backed by a RAG system, and the other one is LLM just trained for example, healthcare application. The other one just trained for function calling and tool use for a specific use case. So in the mixture of agent scenario, a lot of standalone independent model collaboratively work together. So you just need to route the question to the specific LLM. And this can be just one layer or a graph sort of architecture of many LLMs working together. But when we talk about the mixture of experts, for example, one of the interesting paper was Mixtral. It was one of the first papers released in the field. So we do not have standalone LLMs which are completely independent. So when you look at the transformer architecture, it has different building blocks, and each transformer block has two major parts. One is the feed-forward layer, FF layer, and the other one is attention layer. So what happens is that people were like, okay, if I have a 671 billion parameter model like in DeepSeek, it would be very much expensive that we infer that at the inference time. So what happens is that when the question comes in, by question, it's not question anymore, it's just sequences of token. So for example, it goes through the attention layer, and then we can like expand the number of feed-forward kind of components. So this token would be routed to the specific feed-forward part. So here we, at the end of the day, we have a standalone LLM, but it is modularized. So we have different FF layers working in parallel, and at each inference time, just a subset of them would be activated. And instead of just activating the whole 671, just for example, 1/8 of the parameters would be activated. So it would be a very cost-efficient strategy, especially at the inference time. I hope I answered your question. Are there any other questions? Cool. So if there are no more questions, feel free to reach out. I'm available on LinkedIn, Twitter, and Blue Sky. I'll be happy to discuss collaboration opportunities, and also further discuss the questions around this talk. So thank you.